Okay, in the next video in this unit, we're going to be talking about cells and how they function and relative to diffusion and osmosis, particularly diffusion with neurochemicals from the nerve cells and from hormones that are secreted from endocrine cells in our glands. So to do this, I think the animations in your Chapter 4 PowerPoint are very good, and we're going to look at those first. This one is on diffusion.
Molecules dissolved in a solution are in constant random motion due to their kinetic energy. One result of this motion is that dissolved molecules become evenly distributed throughout the solution. This tendency of molecules to spread out is an example of diffusion. But how do these molecules come to be evenly distributed? Let's start with a beaker of plain water. What will happen if we now add a lump of sugar to the water? A lump of sugar is composed of many individual sugar molecules, and even as a solid lump, the individual sugar molecules are in motion. When the lump is dropped into the water, it begins to dissolve. Individual sugar molecules move randomly and constantly from the area where they are common to the area where they are scarce. This type of motion, when molecules move from areas of their higher concentration to areas of their lower concentration, is called diffusion. Diffusion continues until all the sugar molecules become evenly dispersed throughout the beaker. The rate of diffusion is affected by temperature, size of molecules, and the steepness of the concentration gradient. Although not specifically shown in this animation, this is one of the processes whereby materials are exchanged between a cell and its environment.
Okay, so let's take a look at what we just saw, but let's do it for real with a glass of water. And you've all seen this. There's a point I'd like to make, however. We'll put a little blue food coloring in this water, and then we'll watch it as it starts to move around. This is cold water. If I had hot water, the diffusion of this material, which is a bunch of particles of dye, of blue dye, would be faster than this. The man in the video, the narrator, also said that the rate of diffusion is not only affected by the temperature of the solution, but by the steepness of the concentration gradient. In order for your muscles to work, for example, calcium in your interstitial fluid is 10,000 times more concentrated than it is within your cells, in the cytoplasm of your cells. So the speed at which diffusion occurs a lot faster when the difference between the low and high areas of concentration are the greatest. 10,000 times more concentrated. It's amazing, isn't it? Now, as you watched this happen, it seemed sort of slow, didn't it? It's almost completely diffused now throughout the glass. It's a little bit left that's still more concentrated, but it's getting there. And if I swirl the glass, or if I had a stirrer, which I didn't bring, I'm sorry, I would get it to diffuse. But it's almost there. Now, it does seem slow, but I want you to realize that you couldn't detect the movement of this across a distance of only 1,000th of an inch. That occurred so fast, it was less than a blink of an eye. So you didn't see that. Okay? You couldn't see it. And this is what happens in your body. For example, when CO2 leaves a cell, crosses the membrane, and attaches to a hemoglobin molecule in your red cell, realize what has to happen. The CO2 is at high concentration in the cell. It moves rapidly into the blood, and then rapidly across the red blood cell membrane, attaches to a hemoglobin molecule. At the same time that's happening, oxygen that the hemoglobin molecule is carrying moves just as fast outside of the cell, across the other of the red blood cell, through the membrane of the capillary and into the cell through the membrane of the cell that needs the oxygen to burn the food, like the sugar molecule. That fast. It's rapid, and it needs to be rapid, and it happens billions of times a second in millions and billions of cells. So now let's take a look at osmosis. The only difference between diffusion and osmosis is that osmosis is happening across a cell membrane. And in the case of it moving across a cell membrane, there may be molecules that are too large to move through the membrane. And so there's a tendency to move water. So osmosis is actually the movement of water in response to a concentration gradient across a membrane into a hypertonic solution, which means this is the side where there's a lot more molecules. Let's watch this one briefly.
Diffusion is the net movement of molecules down a concentration gradient. This process allows small molecules, such as oxygen and carbon dioxide, to cross the plasma membrane. Most polar molecules, such as sugars and proteins, cannot freely cross this lipid membrane. Although water molecules are polar, they are small enough to pass through the membrane freely. This special case of diffusion that involves the movement of water molecules across a membrane is called osmosis. If a molecule, such as urea, is added to one side of a membrane, it will not be able to diffuse across the membrane because it is both large and polar. Because of its polar nature, it will interact with other polar molecules, such as the water. This interaction reduces the number of free water molecules on the right-hand side. With fewer free water molecules on the right-hand side, there is now a net movement of water molecules down their concentration gradient to the side with the urea molecules. Because more water molecules are moving into this area than are leaving, the water level on the right side will rise. If the osmotic concentrations of two solutions are equal, the solutions are isotonic. However, when the solutions have unequal osmotic concentrations, the solution with the higher concentration of solutes is hypertonic, and the solution with the lower concentration of solutes is hypotonic.
Okay, so we can think about this with respect to our body fluids and some of the interactions that occur. We'll be talking about that in the next slide. There's a further demonstration we want to look at that you can do at home with an egg, and we'll find that in just a moment. Okay, this is a YouTube video we're going to look at. I'll put it on, get it started here, and then put it back on full screen.
See, what happened is this was the product, an egg, and it's just the membrane of the egg. There's no shell except right here, which can be easily scraped off in water. See, what happened is the vinegar dissolved the hard part of the shell. So now what's left is the thin membrane between the yolk and the oxygen that helped the vinegar to dissolve the shell. So now we're going to see how it bounces. I'm going to show you. And notice how you can very faintly see the yolk inside the egg. Now we are going to scrape the last.
Now we'll see part of a video where that egg, or any egg that was decalcified with vinegar, takes a day or two only, was then put, in one case, this one, into water, pure water. And because it was put in pure water and the concentration of different sugars and salts inside are high, the water moved in to the egg and made it swell. In fact, if you left it long enough, it would explode. On the right, there is an egg that had been put in a heavy sugar solution like molasses and left, and the water got sucked out of it through osmosis. Water moved out because the concentration of sugar in the molasses was much higher than the concentration of sugar in the egg. And this is a pretty dramatic demonstration that you can do at home.
And also, egg A, which is this one here, it now measures 4 15/16 inches around the circumference. And egg B now has swollen approximately 1/8 of an inch to measure 6 inches around its widest part. Well, folks, there you have it. It seems as though sugar potentially absorbs water, thus maybe if you go out for a heavy night of drinking, you're drinking nothing but rum and cokes all night, the coke and extra sugar will kind of dehydrate your body, perhaps causing hangover. And here you can see the effects of just straight up water on this egg here. This concludes my experiment.
Now we'll look at one more illustration with blood cells. And again, you have a good animation on your PowerPoints to show the difference between water moving in and water moving out, in this case, red blood cells.
The image on the left is human erythrocytes, or red blood cells. The image on the right is enhanced with filters. These living cells are in isotonic solution. Note the lozenge shape. Now the solution has been changed to have a high salt concentration. It is hypertonic. The red blood cells shrivel and become crenated. Finally, the solution has been changed to plain water. The cells swell and burst, leaving empty membranes behind. This phenomenon is called hemolysis.
Okay, so these are very important phenomena, both diffusion. Sometimes there's facilitated diffusion, such as when a molecule like insulin attaches to the cell and opens a gate so that sugar can get into the cell. When that doesn't work, we call that diabetes. And osmosis, which is very important in the water balance and electrolyte balance, as it operates through the nephrons of the kidneys. When you take other courses, such as anatomy and physiology, you should learn more of this. But it's important to understand what's going on, to understand what diffusion is and what osmosis is, and with respect to diffusion, to understand that it can happen so fast that it's faster than a blink of an eye. And this allows your body and its billions of cells to do things for you automatically and quickly so that your cells and tissues all function correctly.